is the plan for the talk. Uh, so I will try to talk this part today probably about Orbifolds. And number 17, this is a beautiful, well-known story. And then maybe I started a bit with its relation with string theory. Everything from a very elementary point of view. What is an orbifold? Well, first, there is a manifold. What is a manifold? The whole point of a manifold is that these maps are smooth and this is smooth, and they are. But there is a point that could or could not be added to the definition of a manifold. It's added to make it a manifold. That the maps are one-to-one. But of course, you could consider maps that are not one-to-one. Then you would get something slightly more general, and you could ask to have a little bit of order in this not one-to-oneness of these maps. That these maps, that the map from here to here is a quotient of a ball by a finite group. Then, of course, when you are trying to do these things, well, you get this complicated thing when you want to go from here to here because this is already a quotient, so many go to one. So you get a lot of disconnected, possibly things here to this intersection. And here you could get disconnected possible things here to this intersection. Then when you're trying to go to here, it gets confusing. So the gluing gets a little bit more complicated, and it can get incredibly confusing, in fact. But anyway, this is an orbifold chart. From the naive point of view of if you insist in putting this in the Procrustean bed of manifold theory, then you end up with a singularity. But from the point of view of this orbifold world, this is a smooth space. I'll try to emphasize this, explain this in a minute. So anyway, this is a chart. This is a smooth chart. This is smooth action. This is a group acting smoothly on B. And the quotient happens to have this corner here. For example, it was rotation of this disk by a 45-degree angle. Then you would feel that you have a cone here. And this you would feel this kind of tip of the cone as a singularity from the naive manifold point of view. If you see you put a metric here, this metric either explodes here, or if you put another device here, this device tends to explode here. If you forget about the chart, you just think of the final space. In any case, we have an example. You could glue these things, northern hemisphere, you could glue this one here. Southern hemisphere, you could glue this one here. And of course, in all these groups are cyclic and abelian, is not by any means a stretch of the imagination the most general case, but it is a case. And then you glue this one here, and then you get here a space that it's a weighted projective space, but here it's called a 3,4 football. American football, not soccer. More generally, the weighted projective space, that is an archetypical example of these circumstances is you get a weight, there's a bunch of integers, and you get the sphere, and you get the S1 action that depends on lambda, Z acting on Z naught through Zn, is, well, you raise every one of these Z's to the nth power. And this is kind of a weighted Hopf action of S1 honestly. So it gets, if already, the whole thing had this kind of torus knots all over the place, and now these things get even a little bit more twisted as you tend to one of these um, as one of these things that look like singularities in the. Now you say, well, what are you doing here? I don't see finite groups acting on balls. I see a continuous group as one acting on manifolds. Um, but the thing is that one can take so-called slices to to uh, to transform this construction into one of balls acted on by finite groups, not continuous groups. Uh, so one can take slices, just like charts for projective space, just as projective space, when all these are one, projective space can be written in this fashion with all this equal to one. But you can take charts, you can take the various points of view, sending points at infinity in various directions, and you can have the atlas for projective space. It's a linear atlas at that. Uh, well, if you do the same here, you end up with, well, balls, topological balls, you end up with Euclidean spaces acted on by cyclic groups given by roots of unity, given by the various lambdas. The three for football is a particular case of this construction. And more generally, in 1953, Kosul proved a just a second, theorem uh, that this theorem says that if you have a Lie group, compact Lie group, compact is important, acting almost freely on a manifold, and this means that the stabilizer of every point is finite. Then the quotient produces an orbifold with underlined topological space, the quotient. And this is exactly what we just saw here. This is exactly this. And this is called Kosul's slice theorem. And just to mention an interesting story is that there was the question as to the converse open since 1953. Is it the case that every orbifold can be written as a manifold divided by a compact Lie group? Where an orbifold is something that has local charts like this, but we don't know this representation. Can we, from this representation, get a like this? Well, we can, but the question was uh, 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 interesting because we know we can't for even for an arbitrary football, we cannot put it as a quotient of a manifold by a finite group, the whole thing. A global manifold by a global finite group cannot recover even just any PQ football. This cannot be done. And exercise, especially the students, please try to find an invariant that detects that this cannot be done. A finite group cannot globally act, but there's no problem. A continuous group can globally act, and you get the orbifolds by Kosul's slice theorem. So there was a question open since 1953, is the converse true? And recently, John Pardon almost proved that let's say he proved this is the case with a very sophisticated homotopy theoretical proof, and a year later or so, Enrique Becerra and myself proved the converse. that every orbifold can be written like this. And John Pardon from the Simon Center in Stony Brook and proved this by a method, and we proved it again, Enrique Becerra and myself, by a much more elementary method. It's a very different proof. Our proof is very, very short, and Pardon's is very, very complicated and sophisticated proof. In any case, that was an open thing since 53. Now it's resolved. In these wallpaper groups are interesting. So let's see what they are. The wallpaper is a drawing that covers the whole Euclidean space by repeating a motif indefinitely. This is from Wikipedia. In manner that certain symmetries keep the drawing unchanged. To a given wallpaper, there corresponds a group of such congruent transformations with function compositions group operation. Thus, a wallpaper group is in a mathematical classification of two-dimensional repetitive pattern based on the symmetries in the pattern. Such patterns occur frequently in architecture, decorative art, textiles, tessellations, and tiles, as well as wallpaper, of course. So here is an example. This is a beautiful story. This is an example of Tahiri, and this is in Nineveh in Assyria, and this is in porcelain in China. And one could give Mayan examples. Every civilization felt the need, the human need to create this art, and and we don't need to be told this is from China or Assyria or Tahiri to see the beauty and the pleasure that it gives us to see the thing and to try to explore it with our eyes, and one feels that something is going on here, So that's nice. So the number 17 appears here. There are exactly 17 distinct groups of such planar symmetries. That there is at most 17 such groups was proved first by Egraf Fedorov in 1891, and then derived independently by a, I think, nicer proof by George Polya in 1924. Interestingly, the proof that the list of wallpaper groups is complete. I mean, there is at most, but are there 17 of those patterns? The proof only came after the much harder case of space groups had been done. But of course, this was a silly thing of mathematicians to do, because artists of the classical Islamic civilization had already proved this in La Alhambra, in the south of Spain. Anechoism, as the name indicates, is the absence of material representation icons on both the natural and supernatural worlds in various cultures, particularly in monotheistic Abrahamic religions. The prohibition of the representation of the world, humans, and plants and animals, especially humans, but also animals, very important, motivated the development of very sophisticated decorative patterns in palaces such as the Alhambra, because Islam, like many other Abrahamic monotheistic religions, prohibited the representation of idols, but people need art. So if you go to the south of Spain, to the Alhambra, you'll see a lot of art, but it has to be very abstract so as to not to be mistaken by an idol or an icon. In the Alhambra, there is arabesque designs that decorate everything from the tiles and plasterwork to good carvings and lattice work in the windows. It's absolutely unbelievable. So if you go to Granada, well, when I went to Granada on my way to a conference, of course, I stayed 2 entire days to walk all day in Alhambra looking at these patterns. It's absolutely fascinating. And it turns out that all 17 wallpaper planar crystallographic groups appeared in the Alhambra. So this is a remarkable fact that the 17 patterns have been found by the classic civilization, the classic southern Spain Arabic civilization, much before that people redid the discovery in mathematics. It is also interesting that Spanish is a combination of Latin and Arab, and that's why it's so distinctly different from French or Italian. Anyway, Orbifolds and the number 17. There's a surprising and beautiful proof of Fedorov's theorem using the concept of Orbifold-Euler characteristic. And this is in the classical paper of Conway, the Orbifold notation for surface groups. This proof is due, if I remember properly, to Bill Thurston and John Conway, both of whom I was lucky enough to know and have long conversations with. Unbelievable guys, both of them. Fantastic guys, both of them. And so there is this paper, the Orbifold notation for surface group by Conway, and it has this sentence there, this epigram. Even quite ungainly objects like chairs and tables will become almost spherical if you write them in enough newspaper, it says Conway. So this notation was introduced, Conway says, by Bill Thurston, but it really was in conversation between Thurston and Conway at Princeton. And then among the works of Dutch draftsman Escher, one can find examples of all these 17 groups. And then in Escher, even some of the hyperbolic case, of course. So well, you have an orbifold, you can put a metric, and then you can try to put a metric of constant curvature, all these things that are natural to mathematicians. And then you can try to do this Gauss-Egregium theorem. And we'll come back to this, to get from the number 17 to the number 12, should be called this, this talk. So we have this generalized, the usual orbital characteristic, and there is many ways to define it. I'm going to be lazy and not give a beautiful or motivated definition. Read the paper of Conway Daw. You want to read a beautiful and motivated definition. And then, but you could write the orbifold-Euler characteristic as in this way. Why not? There is definitions, and then you end up with this one. You think about it, all these things. For example, putting a metric and trying to recover the theorem and so forth. It is a rational number, not an integer anymore. This is very important for everything that follows. And In dimension 2, we have this explanation. Let's see if you like it. The other characteristic, this is from Conway's original paper. The other characteristic of an orbifold generalizes the Euler characteristic B minus E plus F of a manifold in the natural way. It is a rational number which coincides with the usual intervalued characteristics for ordinary manifolds without cone points, and whose value gets divided by G when we take the quotient by a discretely acting group G of finite order G. For a map, it can be computed by the usual formula, provided we make proper allowances for the divided nature of vertices, edges, and faces. Namely, a vertex at a cone point of order m counts at 1 over m of a vertex, while a vertex at ordinary boundary point is half of a vertex. Vertex at a type m corner point is 1 over 2m of a vertex. An edge running along a boundary curve is half of an edge. And finally, a face with just one internal cone point of order m is 1 of m of a face. Makes sense, doesn't it? Hello, hello?
Yes.
Yeah, it kind of makes sense. Why not? So, so we have this proof of the number 17 due to Thurston and Conway. A two-dimensional compact connected orbifold has either a hyperbolic structure, a parabolic structure, an elliptic structure. An orbifold is called bad if it does not have a manifold as a covering space, by the way. So we have this situation here. And the 17 parabolic orbifolds are the quotients of the plane by the 17 wallpaper groups. And so by computing the orbifold Euler characteristic, you get to the number 17. This may be too brief, but students, this is an exercise. Recover the number 17 from the observations I have just made, or read the paper of Conway, where he recovers the number 17. I think I gave enough clues to recover number 17 from what I just said. So maybe I continue a little bit. Let me continue a little bit. So again, these were global orbifolds. Remember, this was already the issue, bad, not bad, of whether I can use a finite group globally or not a finite group, even from the beginning of the theory. By the way, the word orbifold was famously invented by Bill Browder. The people say that it was by Bill Thurston, but it was in the Thurston seminar. They were having a conversation. They said, "Well, what are we going to name these things?" And Bill Browder came up with the name of orbifolds and on Thurston seminar at Princeton. But of course, I already mentioned as to what we are going to deal with. That is the problem of gluing different charts. This is, to say the least, somewhat confusing sometimes. And the way to organize these gluings and not get confused is to use a little bit of category theory. So we're going to interpret an orbifold. And let's say right now it's a global quotient, namely M mod G, G, a finite group, only one chart. As a smooth category, whose objects are the points of M, and we insist on thinking of a category where the objects are smooth manifolds. So it's an enriched category. It's a category that the category has a smooth structure. What does it mean for a category to have a smooth structure? It means that the objects are smooth manifolds, that the morphism, the arrows in the category has a smooth structure, smooth manifolds, and that every operation is smooth all along, all together. In any case, a typical arrow of this category is a pair x comma g, and the composition of two arrows looks like this. And so this is a smooth category, and actually it is a groupoid. Every arrow is invertible. Exercise again. It's easy to just write H equals to G inverse in the diagram below and get the inverse. So it's a smooth category, but it's also a smooth groupoid. When a category, every arrow has an inverse, is called a groupoid. So to a groupoid X, we will often associate an infinite dimensional space. Actually, what we're associating is a homotopy type. It's not a space. But it's called its classifying space. Because if the space here was M was a point, if M was a point, then we would have that this would be a group, not a groupoid. The object would be a point, and the arrows would be the group G, point cross G is G, and then we would have point goes to G, point times G, that is point. So there is only one point, but the arrows, there is many arrows, G, H, G comma H, G H, G comma, all this story, the group itself. So a group, when M is a point, this groupoid becomes a group. And this space is the classifying space of the group. Normal Steenrod's classifying space of the group. But more or less to make it concrete, we start by drawing a graph, putting a vertex for every object, for every point in the original space, and an edge for every arrow, for every in the category, for every pair n comma g, and we fill it with a 2 simplex whenever we have a commutative triangle in the category, and with a 3 simplex wherever we have a commutative tetrahedron, and so on. And this is Seagal construction of the classifying space of a category, 1968. And then you get this infinite dimensional space associated to the category, or to the groupoid in this case. Now, if we remember the topology, we really need to remember the topology of x0 and x1 for these to be really the classified space constructed by Seagal in 68. Not think of them as discrete spaces, but remember their topology. And there is always a canonical projection from this infinite dimensional topological space, homotopy type, to the quotient space X, M mod G in the category of topological spaces, so that the inverse image of a little point in the quotient is the classifying space of the stabilizer of the point that is well defined. It's a subgroup of G, fixing X. Let me ask at this point, are there any questions?
So yes, you have BG, but do you have EG?
Yeah. You will have it. It's very easy. You just kind of shift the thing just a little bit.
But is it contractible, EG, or is it? It should be, right?
EG, EG is a contractible thing where the groupoid acts. It's the same thing.
So yeah, that's what makes me a little bit confused. So the subtle difference between EG and BG in this setup.
Well, even for a group, EG can be constructed. EG can be constructed. You can construct this space where G acts freely,
Yes.
and it's contractible, and it can be constructed in this way. But you see, here, rather than started by x0, I destroy x0, and then I start by x1, and do the same construction.
Mm-hmm.
And then I get a contractible space where G acts freely.
Mm-hmm.
It can be done by the same procedure. You construct this big, infinite dimensional, contractible space, and it's easy to prove that it's contractible the way it is constructed, and that G acts freely is also easy to prove, and that the quotient is the thing. Yeah, everything can be proved. Yeah,
Okay.
it's a principal bundle and everything. Yeah, that's the thing. Well, what we just said, for if the orbifold question is dot comma G, this space, topological space, homotopy type, has the property that the set of isomorphism classes of principal G bundles is isomorphic to the set of homotopy classes. So you only need the homotopy type of BG. In fact, BG is not very well defined. The way I did it is very functorial, but what is important is its homotopy type. And here we have the EG that we just mentioned, and this is Steenrod's construction of the situation in the case where M is a point. And if the induction is global, there's no mystery. We just take the EG, and this will give us the BX. You see?
Yes.
So this is like the analog to the EX. If you don't divide by G, M cross EG is the EX, And then you
Okay.
divide. Yeah. In the global quotient case, for a finite group. For a general group point, Ike Murday has a book telling what BX classifies. It classifies something very categorical. Let me not say what it classifies today. It's nice. It's very nice. I like it. Uh, uh, and then if you get equivalence of categories, you would say, well, I have two equivalent categories, what happens with the BCs? And they are homotopy equivalents. So this is extremely important property of this construction that I described, is that if I take equivalent categories, I get the same homotopy type. This is a very important thing. And now, already the Euler characteristic was kind of a bit of a puzzle that returns you the number 17, Thurston Conway. Cohomology is a bit more of a puzzle. What is the cohomology of an orbifold? But I will leave you with that mystery for next time. And I stop right here. Think about it. We want to recover the Euler characteristic from orbifold cohomology. What is going on?
So just one question. So if your manifold is a quotient, or if your orbifold is a quotient, isn't it just equivariant cohomology? It's something. It sounds very reasonable to do this Borel construction, and is it
Yeah,
wrong?
it's a possible answer, but maybe not the only one.
Yeah.
So
Yeah. Well, it would require your theorem, right, to represent every orbifold as a quotient by a group.
that's right. That's right. And we didn't have this term for ages, So you could also think of the cohomology of just this space. Why not? You just do the cohomology of the general Seagal construction for the classifying space. Yeah, you could do that. But you could do other things as well. So we'll go in search of cohomology next time. Okay.
Okay. Thank you so much.
Thank you.